So, good morning, ladies and gentlemen. Welcome to today's morning session. So, we have three speakers in the morning, one speaker in the afternoon. And the first speaker is Stefan Goedecker, who will introduce us to the fascinating world of wavelets and their application to density functional field. Please.
Yes, thank you very much for the invitation to come here. Yeah, I think I have seen a very exciting program, and so yeah, I want to talk about wavelets, which are some kind of mathematical tool, which I think can be useful in lots of different contexts in physics and chemistry. So I have here a title, 4 families, a kind of a subtitle, 4 families and 3 applications. So don't worry, it's not a soap opera. I will not talk about the Denver family. But yeah, wavelet is a very generic name, okay? So if you say that you're using wavelets, actually people will not really know what you're using because in this big class of wavelets, yeah, you have those so-called families, so different kind of types of basis functions. And then actually within a so-called family, you still typically have members of a different degree of or different order, like also in finite elements, where you can have linear finite elements, quadratic finite elements, and so on, where you can increase the order to improve certain properties. So there's a huge zoo of families of wavelets. So I have picked out of this big zoo, I have picked 4 of them. Namely the Haar wavelets, the Dobeschi wavelets, then the interpolating wavelet, and finally multi-wavelets. And then the Haar wavelets, actually I will introduce them only to explain you the basic workings of wavelet theory, which is also frequently called multi-resolution analysis. And then concerning the remaining 3 families, I will show you certain applications. So here the Dobeschi wavelet, for instance, we use them as basis functions in our big DFT electronic structure code. Then the interpolating wavelets are the basis function in our Poisson solver package. And then finally with multi-wavelets you can do all electron calculations to get extremely high accuracy atomization energies. Yeah, okay, let's start. I mean, all families of wavelets have certain properties which they share. And so I think a very important property is that wavelets are typically localized both in real and in Fourier space. So if you do a Fourier analysis of a signal, right, of course you know you have only frequency information. You lose any kind of information at what time, for instance, you have high frequency, or at what point in real space you have high frequency. So if you have, for instance, a signal of this type, right, and you see frequently here in this left half you have a longer wavelength, right, things are oscillating more slowly. Here things are oscillating more rapidly. And if you would do now a wavenet analysis, that means a multi-resolution analysis of this signal, then I mean within wavelet theory you would immediately very easily see that, yeah, here in this region you have a slowly varying signal, and here you have a very rapidly varying signal, right? Because essentially those basis functions, the wavelets, they have a finite support, so they extend only over certain regions. So you necessarily, because of that, you analyze only a certain interval. Yeah, then another extremely important property is that wavelets form a so-called systematic basis set. What does it mean? I mean, for a mathematician, I think a basis set that's not systematic is actually not a basis set at all. But in physics and especially chemistry, people are frequently using certain basis functions, which they call nevertheless basis sets. And they can be problematic in the sense that if you increase the number of basis functions, it's not guaranteed that you get a more accurate solution. Whereas this kind of property is guaranteed if you use a so-called systematic basis set. I mean, like the most famous examples are, of course, plane waves, right? You know that if you increase your number of plane waves, that means if you increase your cutoff energy, then you will get your result with higher and higher precision. Of course, the result means within a certain model, approximation model like density functional theory, but within this model, you will get it more and more exactly. And it's guaranteed, so you can kind of ask for a certain accuracy, some certain epsilon, and then you can find a number of basis functions such that you get this epsilon of accuracy in your calculation. Okay, so wavelets have this property. And I think the third most important property is that you can have adaptivity. So here, of course, you can recognize that some kind of sketch of some kind of molecule, right, where you have some kind of 6 ring. And now, of course, you know, if you want to do some all-electron calculation, right, then those core electrons are extremely strongly localized. So you will need very, very high resolution here around the atoms. Whereas, for instance, in the region here, you have just an exponentially decaying wave function, which is slowly varying. And there, of course, you don't need high resolution. So here, I have now introduced some kind of grid to indicate the regions where you have high resolution and low resolution. Of course, wavelet theory is not something like finite differences where you use functional values on a grid to do your calculation. But as we will see in a moment, actually, nevertheless, you need always such an underlying grid because you put those basis functions, so those scaling functions and wavelets on each grid point to construct your basis set. So you can actually have here really an arbitrary number of resolution levels. So if you want to, you can have, I don't know, a resolution that's 1,000,000 times larger here around the nucleus compared to a region that's far away. Yeah, okay, now how do we get our basis set? I mean, first of all, even people always talk about wavelet theory. Actually, a wavelet family is characterized by 2 fundamental functions, which is the so-called scaling functions and the so-called wavelet. And in a certain sense, actually, the scaling function is more fundamental because it turns out that you can write any wavelet as a linear combination of those scaling functions. Yeah, so now to get a basis set, you consider all translations and dilatations, right? Translation is obvious. Dilatations means that kind of you compress your wave function. So that's this index k here, right? If k is large, then this function will vary rapidly. That means it has high resolution. Okay, and therefore, okay, if it's varying rapidly, right, it kind of corresponds to high frequency Fourier components. So we can say k is some kind of measure of in Fourier space. Whereas the j, right, is just the point now on, let's say, on this Cartesian grid that I have shown before, where this wavelet is localized. Yeah, okay, and then here we, as I told you, we have, yeah, first of all here the wavelet, and then the other function here, this scaling functions, which is, as I said, actually equally or perhaps even more important. Another property that's shared by all those wavelets families is what's called the refinement relation, which means that whenever you have either a scaling function or a wavelet on a certain resolution level, you can write it as a linear combination of wavelets or scaling functions at a higher resolution level. So you see here, right, I have this factor 2. That means I have now here a resolution level, a high resolution level, right? Here I have exactly doubled my resolution because, right, the basis functions are compressed by a factor of 2. And so, yeah, so that's this general refinement relation. And you see that we have here certain coefficients. And actually, numerically, if you construct, for instance, if you want to plot or construct a scaling function of wavelets, typically you start just with those coefficients here. And once you have those coefficients, actually, you can construct everything. Yeah, now let's start with those Haar wavelets, which are conceptually by far the simplest wavelet family, but which are kind of useless for many applications like solving partial differential equations because they are not smooth enough. So here, actually, you see the 2 fundamental functions, scaling function and wavelet. And well, you see here the function is discontinuous. It drops from 1 down to 0. So, of course, you cannot use it to solve differential equations. Yeah, okay, now let's assume that we have this function here. Let's say we consider the interval between 0 and 1. And now we have a function that consists of 16 such plateaus. And now we go on resolution level 4, right? That means we kind of compress this master scaling function by 2 to the power 4. And well, then that will give, now on this resolution level 4, that will give this scaling function. And then, of course, it's obvious that here this piecewise constant function can, of course, exactly be represented by a linear combination of those scaling functions, right? And the expansion coefficients that I have here, in this case, of course, are just nothing but the functional values on each plateau. Yeah, okay, so that's it. That's now the so-called scaling function representation, and it can already be quite useful. But then now you have this alternative, the so-called wavelet representation. Yeah, as we have seen, right, already before in the Haar wavelet family here, that's what the wavelet looks like. And now, of course, we have seen, right, we can compress it to get high resolution. And in this way now we get here, well, we get a first wavelet, then 2 more, 4 more, and finally 8 more. Yeah, and I think it's also clear that kind of, if you count them, actually here again, I have 16 functions. So the number of basis functions is identical to what I had before in the scaling function representation. So it's not clear at present what the advantage really is. And you see that kind of this one remaining or surviving scaling function is something like the zeros Fourier component in Fourier analysis. It just gives you the average value of the function over the whole interval. Again, let's say it's the interval between 0 and 1. And then, yeah, okay, here kind of this first scaling function then tells you the difference kind of between the left-hand part and the right-hand part of your function, and so on, right? And of course, you see here then as the highest resolution wavelets, again here, the length of the plateau is 1/16, so we can exactly represent the previous function, right, that we had here. And so we can then write down here this expansion, right? So here I have the scaling function in red, then here's the first wavelet, then here's the second wavelets, and so on. Yeah, okay, so as I told you, also we have now 16 wavelet basis functions. So what's the advantage? Well, the advantage is if you go back here, then for instance you can just add some wavelets here in this left-hand part of your interval to get the desired resolution. Okay, so that's kind of the basic, most basic point of wavelets. Now let's come to the representation of operators. So, of course, if you want to solve partial differential equations, we have to set up operators. And yeah, there are now 2 forms. I mean, the most straightforward thing is the so-called standard operator form, which is shown here. Okay, so you see here whenever things are dark, that means you have matrix elements that are non-zero, and then here you have 0 matrix elements. Yeah, and I mean, how do you get this structure here, right? So you see here, in this vector here, you have the expansion coefficient. So you have here the the expansion coefficient of the single scaling function. Then here the expansion coefficient of the first wavelet. Then here's the second 2 wavelets, the next 4 wavelets, and finally here's the 8 wavelets again. It's the highest resolution level, right? It corresponds exactly to what I have shown here. Okay, and now of course you see here the first scaling function, the first wavelet, right, they extend over the whole interval. That means they will overlap with all other wavelets here, even in the kind of best case where your operator is local, something like if you want to calculate something like the kinetic energy. And well, that explains, right, why here in those 2 lines, for instance, are full, right? There are no zeros there. It's just here I have every non-zero matrix elements. Whereas then, for instance, if you go to here, matrix elements coupling different wavelets at the highest resolution level, then of course you see this wavelet here doesn't overlap with this one here. And therefore, for instance, here you have large regions that are filled just with zeros that are empty. Okay. So what we have here is, you see, we have a coupling between resolution levels, right? I mean, for instance, right here, this part here is coupling the highest wavelet resolution level with the lowest wavelet resolution level. And yeah, I mean, this form is more or less the straightforward form. That's why it's called a standard form. And yeah, I mean, you can set it up. It works fine if you have a limited number, let's say, of 2 resolution levels. But if you have now a very large number of resolution levels, then actually it becomes very complicated and numerically inefficient, because actually the number of non-zero entries is quite small. Yeah, now there is a second possibility. I don't explain all the details. That's called the non-standard operator form. And it's kind of in spirit very similar to probably some other methods that you know already from, let's say, computational physics, such as perhaps the fast multipole method, where you have to calculate some kind of redundant data. And then with those redundant data, actually, in the end, you can obtain your desired result more rapidly. And that's also the case here. As I told you, I will not really go into the details. But what you see here, right, you see here that we have a redundant data set, right? In principle, we would need only here the scaling function expansion coefficients, and then here all the wavelet coefficients, which are denoted by D. But you see we have also here, we have still also those S values. So that means we have here on this resolution level, we also have a scaling function representation in addition to the wavelet representation. And that's why this vector is actually redundant, but it turns out that if you choose this redundant form, then actually the matrix is getting much, much simpler. All of a sudden, you don't have anymore a coupling between different resolution levels. Well, in order to generate this redundant data set, you have to do some additional work. So the prefactor is higher than for the standard form. Well, also what is needed here is kind of that the transition between different resolution levels is kind of slow, that you don't very abruptly go, for instance, from the highest resolution level to the lowest. But if those conditions are satisfied, then actually this non-standard operator form should be used and is the most efficient one. Yeah, okay, so that was now just the first family. Now let's come to this very famous Debussy wavelet family. Yeah, so it goes back to a paper by Ingrid Debussy in 1988, which is entitled Orthonormal Basis of Compactly Supported Wavelets. And actually kind of the basis functions that she proposed in this paper were thought not to exist by mathematicians before this paper. And yeah, so what mathematicians thought that would not be possible to achieve is to obtain a basis set that has at the same time compact support. That means it is strictly zero outside a finite interval. Then that this basis set is orthogonal, and that it has a certain number of continuous derivatives. So those three properties were thought to be incompatible. And if you think about all the other basis sets that you know, like plane waves or so, you'll see that none of them is satisfying all those three properties. Yeah, so that was a real breakthrough in mathematics, and especially the fact that this basis set is orthogonal, of course, makes it useful for electronic structure calculations, because, of course, we know that our orbitals always have to satisfy those orthogonality constraints. So Debussy wavelets also combine the advantages of kind of the two most popular basis sets, namely plane waves. So like plane waves, they are systematic and orthogonal. They are localized in Fourier space, which means that, for instance, you can take over many of the well-established preconditioning techniques from plane waves. And like Gaussians, they are localized in real space. So that means if you have an open structure where you know that in a certain region of space you don't have any charge density, then you don't have to put basis functions in this region. Yeah, then also localization of the basis function, of course, is very useful to obtain linear scaling. And then, yeah, we have this adaptivity. That means we can, for instance, we can do all electron calculations in a wavelet basis set. Yeah, okay, now let's look at some of those Debussy basis functions here. Okay, here you have now, again, as we know, we have two functions right here in red, the scaling function, and then in blue the wavelet. And well, if you look at that, probably you would say that's completely useless as a basis function. That's this kind of ugly thing, right? You see here, actually, it has even a discontinuity in the first derivative. But actually, it turns out that by forming suitable linear combination, all those kind of discontinuities go away. And you can, for instance, with this ugly guy, you can represent polynomials up to degree 4 exactly. Okay. Yeah, here also, of course, again, you see the wavelet is varying kind of more rapidly. So the wavelet is giving you more resolution than the scaling function. Okay, so in principle, that those Debussy-4 wavelets could already be used as a basis set for partial differential equations. But of course, as I told you, we can now go to a family of higher degree, and that's what we do. So we use actually, in the big DFT electronic structure code, we use Debussy wavelets of degree 16, which are shown here. So they look now kind of rather nice. They are fairly smooth. I mean, they still have some rather high order derivatives that are not continuous, but it doesn't bother us. And also you kind of understand probably if you look at this picture kind of the name of the name wavelet, right? It's essentially it looks like a little wave packet. Yeah, with those Debussy 16s you can represent polynomials up to degree 16 exactly. And that means actually that you get a convergence rate of h to the power 14, where h is now kind of the distance between the different wavelets or bases. So essentially it's kind of the grid spacing of the Cartesian grids that I have shown you before to illustrate kind of this adaptivity that you can achieve in wavelet theory. Yeah, okay, I think I will concentrate mainly on the mathematics. Nevertheless, perhaps let me just briefly mention here that, okay, we have developed this big DFT code, which is now solving the Schrödinger equation in this Debussy 16 wavelet basis. What is nice about wavelets is you can very easily switch to different boundary conditions, like without any major change in the code, like we can go from periodic to non-periodic boundary conditions. Well, we have coupled it like many other codes to the libxc code to do all kind of exchange correlation functions. We use it a lot for local geometry optimizations and global geometry optimizations. So we have implemented rather efficient methods to find local minima, saddle points, and to do global structure prediction. We have implicit solvation models to model dielectric environments and electrolytes. There's a linear scaling versions. Of course, you can do vibrations, Born-Oppenheimer, MD, collinear, nonlinear magnetism. We have added empirical van der Waals. Yeah, and finally, I mean, it's also rather well optimized code that kind of can exploit massively parallel architecture quite well, and actually can also exploit GPUs quite well. Okay, now let's come back to our wavelets. So of course now, if you want to do an electronic structure calculation, we need basis functions in 3 dimensions. And okay, you can now form a 3-dimensional scaling function wavelet basis here as shown as I have shown here. So now you have one scaling function which is a product of 3 one-dimensional scaling functions, and then all the other 7 possible combinations, actually they are now called wavelets, right? Because they give at least along one direction high resolution. Like here, for instance, right, I have replaced the scaling function along the z direction by the wavelet. So that means here, this first wavelet will have higher resolution along the z direction, right? Then here, for instance, I will have higher resolution along the y direction, and so on. Okay. Yeah, as I told you, in principle, you can have an arbitrary number of resolution levels. In the big DFT code, actually, we use only 2 resolution levels because we decided that we want to use pseudopotential because they are perhaps the simplest way to include relativistic effects. So that means we have here, like as shown here, I mean, we have a grid. So all those, okay, first the green points, right, they represent some kind of cluster, I don't know, silicon cluster, something like that. And then here, all those grid points, now they have 2 different colors, they are red or black. And red means that we are in a high resolution region where each grid point now is carrying one scaling function and then the 7 wavelets that we need in 3 dimensions. Whereas here in this outer region where we have black grid points, actually each grid point is carrying only a scaling function, right? So the resolution is exactly doubled here in this red region, kind of where we have chemical bonding, whereas here in the tail region, where the functions are decaying slowly, we have only scaling functions. Yeah, just to illustrate you kind of how different the mathematics of wavelets is compared to more traditional basis sets, let me just briefly outline, for instance, how you calculate the kinetic energy in a wavelet basis set. So let's just assume we want to calculate the second derivative operator for the one-dimensional case, right? Between two scaling functions, one centered here at the origin, and the other one then shifted to the grid point I. And yeah, what you then do is the following. Okay, so again here I have just repeat what I want to calculate. And then in a first step now we use those refinement relations, right? So we express now this scaling function by a linear combination of scaling function on a higher resolution level, right? I have this factor 2 here and 2 here. And right, in the refinement relations, we have those coefficients h, and so they enter here. Yeah, okay, then you do a few simple algebraic manipulations, right? You introduce new variables, you shift everything, yeah, okay. And then if you look at those equations for a while, then actually you will see that what is written here is nothing but an eigenvalue problem. And for a certain matrix Aij, and okay, you can write down this Aij, right, in terms of those expansion coefficients h. And you have to search for the eigenvalue of this matrix that has the value, yeah, here 2 to the minus 2, okay, 1/2 to the power 2. Yeah, that's kind of surprising, right? I mean, so you don't use an integral table or something like that to calculate this integral, which represents the kinetic energy. Instead, actually, you have to find the eigenvector of a matrix. And then this eigenvector, right, this eigenvector, yeah, contains those integrals. And once you have it, right, then you can apply it as a filter to calculate your derivatives, right? It's, I mean, the structure is more or less the same as in a finite difference, right? There you also have certain coefficients. You have a filter that you apply then on the real space values of your function. Here you apply your filter on the expansion coefficients with respect to this Debussy wavelet basis. But in both cases you have to do the same operation, right? You have to do a convolution of your wave function with this filter to get then the kinetic energy applied onto this wave function. Yeah, of course, those filters here, right, they have finite lengths, right, because the basis functions have finite length support, they have compact support. So that means this operation here has linear scaling. So if the length of the filter is L, then in the three-dimensional case, right, if you have a grid of n1 times n2 times n3 grid points, in each grid, again, point is carrying a basis function, then that's the operation count, right? So it's linear with respect, because n1 times n2 times n3 is just your number of degrees of freedom. Okay, so that was second wavelet family. Now let's come to the third one, which are interpolating wavelets. So what are the special properties of those interpolating wavelets? Yeah, they have compact support. What kind of an aspect where they are performing better than the Debussy wavelets actually is they have many more continuous derivatives for given support lengths, right? So we have seen before this Debussy 4 looks kind of ugly. Those, I mean, even the low order interpolating wavelets, they look kind of nice already because they have many continuous derivatives. And another important point is that there is a trivial transformation from real space data to a scaling function expansion because the expansion coefficients are actually just the real space value. Well, they are not orthogonal, but if you just want to solve like Poisson's equation, partial differential equation, actually that's not really necessary. Okay, how do you construct those interpolating wavelets? I mean, I will explain you that because it's relatively easily. Actually, I didn't explain you how to construct the Debussy wavelets because that's actually fairly complicated mathematics. So, okay, in order to construct an interpolating scaling function, you start with a Kronecker delta set. That means you have 1 at 0 and then 0 at all other integer points. Okay, first of all. Okay, and then you start a recursive interpolation, which means that in the first step, now you try to calculate values at all half integer points, like here 1/2, 3/2, 5/2, and so on. And if you construct now the lowest order interpolating wavelet, then you use linear interpolation, and that means you will get, for instance, this point here, 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 okay? Okay, then you do it recursively, right? In the next step, you calculate now all functional values on grid points that are a multiple of a quarter. So here, like here, 1/4, 3/4, and so on. And of course, if you do linear interpolation, well, you get those values here. So, okay, I think you see how it works. If you do that really recursively until you get tired, then you'll get just this very simple function, right? A function that linearly grows here from 0 to 1 and then goes back to 0. Okay, now of course you can do the same procedure also with a higher order interpolation scheme, and then, for instance, you get functions which look like that. So here, an interpolating scaling function of order 14, and you can even go to extremely high orders like 100. Okay, they all, I mean, you see all those, also as a higher order, functions have the property, right, that they are 1 at the origin, and then actually they are exactly 0 at all other integer points. This property always remains. And also, even so, those functions were constructed by polynomial interpolation. Actually, they cannot be represented by polynomials, right? They cannot. All those wavelets that I have shown up to now cannot be represented by simple analytical functions. Yeah. Okay. Now, how can you use those interpolating scaling functions to solve a problem in physics? You can, well, we use it to solve Poisson's equation. And yeah, typically, if you do a numerical calculation, your input is some density, charge density rho, which is given on a Cartesian grid, right? That's here shown here. So this rho ijk is the charge density on a 3-dimensional Cartesian grid. And then actually it turns out that, yeah, here, those values here are also the expansion coefficients, just if you want them to represent this discrete charge density by a continuous function using those here now interpolating scaling functions. So those three guys here are interpolating scaling functions. Actually, you see, because of the property that I have just pointed out, right, because those scaling functions are 1 at the origin and 0 at all other integer grid points, you see immediately actually that this condition here is fulfilled, right? If you evaluate rho of r at a grid point, then you will get back those rho ijk's. Yeah, for electrostatics, of course, we know that the multipoles are very important. And yeah, here, another very useful property of those interpolating scaling functions is that kind of this transformation where you go from a discrete charge density to a continuous charge density is conserving your multipoles. So, of course, you can calculate a multipole for a continuous charge distribution in this way, right? And you can calculate it for a discrete charge density in this way, and then actually you can show that those two expressions here are identical. Well, if you use this relation here. Okay, now, of course, in principle, when we have now, if we have our charge density, right, then we can calculate the resulting potential as an integral. We have to use a Green's function, 1 over r minus r prime, to get the potential. And that's what I do here in this equation here. So again, now this V I1, I2, I3 is electrostatic potential that we want to calculate again on our Cartesian, equally spaced Cartesian grid. And our input, right, are those rows. And then you see all we need are those integrals. So those integrals do not depend on the charge density, so I can calculate them once and for all. And then you see that we can go just by this simple equation from the charge density to the potential. We have to do a convolution with this guy here that typically you would call a kernel. Okay? So you see you have to do a convolution, and we know we can do a convolution with FFT techniques with n log n operations. So that means with n log n operations we can go here from a charge density to the potential. Okay? That's the same scaling that you obtain in plane waves with periodic boundary conditions, but here actually you can obtain it for kind of any boundary condition. Actually what we have considered here, right, are actually free boundary conditions. Yeah, okay, so that's a basic idea. I have shown it, right, as I told you, for free boundary conditions, but we can calculate the Green's function also for of course, periodic boundary conditions, surface boundary conditions, also via boundary conditions. And that means actually that because we have the exact Green's function for all those boundary conditions, we can treat without any problem charged clusters, for instance. We don't need something like compensating backgrounds. We can describe dipolar surfaces or clusters or surfaces also in electric fields, for instance. Yeah, okay, a second application of this Poisson solver package, well, actually this kind of whole big DFT package, right, is actually subdivided in libraries. And so one of those libraries is as I told you, this Poisson solver library. And then on top of that, there's now this library to do hybrid functional calculations. And yeah, probably, I mean, you have seen that presumably already, right? If you have a hybrid function, you have this so-called exact exchange term, and this exact exchange energy is given by this expression here, right? And of course, you see again, we have this 1 over r minus r prime kernel, so the Green's function that we have just considered before for the solution of the Poisson's equation. And you can consider that again as some kind of solution of the Poisson equation. You can say, well, I have a charge density rho ij, which is given by the product of those two wave functions, and then I have to find the resulting potentials for all possible values of ij. Well, then you have still symmetries, ij and ji identical. That means that in the end, if you just evaluate the exact exchange energy by this formula, you have to solve the Poisson equation n times n minus 1 over 2 times, right? That's, of course, that's a lot if you have many orbitals. And that makes such calculations rather expensive. But if, I mean, people believe that kind of those hybrid functions are quite accurate, so probably people would be ready to pay the price for that if it could be done faster. And yeah, we have now implemented actually this Poisson solver on GPUs. And in this way, actually, we get extremely high speed. I mean, the basic principle is rather simple, right? We have to solve essentially Poisson's equation, and I have shown you before, it boils down to a simple convolution, okay? The convolution, we do it with FFT techniques. So that means essentially we have to call a FFT, and of course you have efficient FFTs for GPUs in the CUDA library. And so, yeah, that means we can do actually everything on the GPU rather easily. And that's, of course, that's important because, I mean, GPUs give very high speed, but if you have to transfer your data very frequently from the CPU to the GPU and back, then you lose a lot of performance because this transfer is rather slow. I mean, once your data is on the GPU, the calculation is fast, but the transfer to the CPU and back to the CPU is kind of slow, and therefore it can sometimes not be worthwhile to do the calculation actually on the GPU. But in this case, because I mean we have such simple operations, we can really do everything on the GPU. In addition, okay, we overlap computation with communication, and we use actually this so-called direct GPU communication, which results in a significantly higher bandwidth because the data are directly exchanged between the CPUs. They don't have to go over all kind of buffers in the CPU. Yeah, okay, here just some timings. Perhaps let's just look perhaps at this graph here because they all show similar results. It shows, okay, here, I mean, first of all, you see the speed as a number of computing nodes for different systems containing up to 1,000 atoms. And perhaps what's most interesting just here is this gamma here. So that's the ratio between the timing that you need for a hybrid functional calculation, PBE0 in this case, compared to the time that you need for a PBE calculation. And you see that this ratio is it's perhaps, of course, it depends on system size because the scaling behavior is different for small and large systems. But you see it's in the range perhaps of it here. In this case, it's not more than 4. Here, it's not more than 7. So actually, with this implementation, kind of PBE zero calculations become affordable also in a systematic basis set. And yeah, I mean, also here it's essentially it's a brute force the implementation. It's not based on any approximations where you kind of cut off, introduce certain cutoffs, and that means, for instance, that we have perfect energy conservation. I mean, like here you see molecular dynamics run both for the PBE and PBE zero function. So here are the fluctuations in the energy, and then that's a fluctuation in the total energy, which of course should be zero in principle, but because of a finite time step, of course, it's not exactly zero, but you see there's no drift, and it's of the same quality in both cases. Okay, I think perhaps I'll jump over that. Good. Yeah, so that brings us to the end of this part on the Poisson solver based on the interpolating wavelets. So just here still a few features. So this Poisson solver can solve Poisson's equation both for a constant and spatially varying dielectric constant. It can also solve the Poisson-Boltzmann equation. Yes, as we have seen, we have all standard boundary conditions. Yeah, input and output are given on an equally spaced Cartesian grid, and therefore actually also you can couple it to other electronic structure codes, which have typically the same kind of data distribution. And yeah, we of course, once you have exact exchange, you can couple it through the libxc library to various different functionals. Yeah, okay, now let's come to the last family, multi-wavelets. Okay. Yeah, what are the properties? So those multi-wavelets, again, have compact support, but now a big difference is you have here several basis functions per support interval. Before we had always only one. They are also orthogonal. Actually, they also can be symmetric. They have also many continuous derivatives in the interval. But at the end of the interval, of course, they can do more or less whatever they want to do. And so if you use them as a basis set for solving a partial differential equation, actually it's not guaranteed that your solution is continuous. For that reason, actually, yeah, you cannot really define differential operators. The only thing you can use in this case are integral operators. And therefore, you have also to solve then Schrödinger's equation is an integral equation. Yeah, but that's not difficult. I mean, just let me show it briefly. What can you do, right? I mean, just let's write down the well-known Schrödinger equation, and then just, okay, this term with the epsilon, I can bring it over here. This term of the potential, I bring it over here. Then I get that. And then you see now we have this operator, del squared plus 2 epsilon. That's the so-called Helmholtz equation. And then we know that the inverse of this operator is actually this operator, right? I mean, for instance, you see immediately if the epsilon is 0, then of course we are back to the Poisson equation, and then 1 over r minus r prime, of course, is a Green's function for electrostatic problems. And here, okay, we still have this additional exponential term. And then that means we have found a solution, for instance, if kind of this equation here is satisfied, right? Applying now this inverse operator, let's say on some kind of old wave function, I get a new one, and if those two agree, then I found my solution, and of course I can build kind of some kind of iterative scheme on this integral equation. Yeah, okay, so those multi-wavelets are now used in a code which is called MRChem. Actually, this code is developed in the group of Luca Frediani in Norway by Stig Jensen and other people. It performs non-relativistic all-electron density function calculations for LDH, GGE, and hybrid functionals. It allows for an arbitrary number of resolution levels. That, of course, then requires to use what I have introduced before, this kind of non-standard operator form. And yeah, in particular, I mean, with this code, really, you tell the code you want to have your total energy, I don't know, with an accuracy of 8 decimal places, and then it will automatically adjust all the grids in such a way that you get this preset accuracy. There's another code, actually, which is even older, which is called Madness. It's based on the same principles. I don't know, we also tried it out, this code, a few years ago, and it was so unstable that it was kind of, you couldn't get the desired result. I don't know, maybe it has improved now. But anyway, now this guy, Stig Jensen, I think he did an excellent job, and I mean, he really can calculate now more or less anything. Yeah, okay, it's, I think, a relatively new code, right? It still has not many other features, but it's under development. Yeah, okay, so let's come to the accuracy of DFT calculations. I mean, everybody here probably in the audience is doing DFT calculations. And then in your paper you write, well, we calculated this and this property for the PBE functional. And you assume that kind of choosing the PBE is the only relevant approximation that you did. But that might actually not be true. I mean, perhaps you're not aware of it, but probably all electronic structure codes, they use still other approximations. As such, they have certain basis sets or pseudopotentials. So I think you heard about this effort already. There was this so-called delta test set effort, where many people in the electronic structure community kind of came together and tried actually some rather trivial. They tried to get the same energy versus volume curve with different electronic structure codes. Okay, I mean, in principle, you should, of course, get the same result. It turned out initially people didn't get it, and they improved things, and finally actually they got it. And actually that was considered such a big breakthrough that actually it made this publication made it into Science. Okay. Nevertheless, what I want to show you now is, I think this test, was a first step, but it's a very easy test. And if several electronic structure codes give the same energy versus volume curve, it doesn't certainly not guarantee you that you will get the same result for any other properties, like, for instance, the atomization energies. Yeah, but if you want to say kind of what is the correct atomization energy, of course you have to have highly reliable and accurate reference values. And that's actually just what we did now in a collaboration there with a group of Luca Frediani and also Volker Blum. We calculated, actually we generated a test set of nearly 300 molecules, and then we calculated with this multi-wavelet code, we calculated the atomization energy with micro hardware accuracy. So that's at least a factor of 100, perhaps even 1,000 better than kind of the previous calculations. Okay, so then in the next step, we started to examine now the accuracy kind of standard approaches. And well, there are kind of two, as I said already, kind of two main suspects that could have an influence on the accuracy of the result. One is the basis set, and the other one is a pseudopotential, in case you use a pseudopotential code and not an all-electron calculation. Yeah, let's look at this figure that has a lot of data. I mean, first of all, here in the left-hand column, we have PBE results. Here we have PBE 0 results. I think we can look only at the PBE results because PBE 0 has kind of the same behavior. Here we have total energies, and then here atomization energies, which are different than total energies. I mean, in most cases, in electronic structure calculations, we are interested in differences, and therefore, probably this panel here is much more important than this one. Then in this panel here, you see actually the error in the dipoles. And the dipoles are kind of a representative for a non-variational quantity, which typically converges more slowly with respect to the size of the basis set than the variational quantity, which is, of course, the energy. So what do we see? I mean, first we have here now always results for Gaussian basis sets and then numerical atomic orbitals from the FHA Ames code. If we look for, okay, let's perhaps look first at the Gaussians. Of course, a widely used basis set, for instance, is this 6C1 basis set, or also then those double zeta basis sets. And you see that here actually the mean errors are really high. I mean, they are kind of around 10 kilocalorie per mole. So that means actually even the mean errors are probably in those cases larger than what in principle you could obtain with a PBE function. I mean, there you find values in the literature of something like 7 kilocalories per mole as intrinsic accuracy of the PBE functional. And then if you look at the outliers here, I mean, it becomes even worse. I mean, because of the basis set in some cases, I mean, you can have errors in the atomization energies which are, close to 100 kilocalorie per mole. Yeah, then, I mean, if you go to very large basis sets like here, a quintuple setter, of course, things improve. On average, you are here well now below this famous chemical accuracy of 1 kilocalorie per mole. That's certainly probably enough for more or less any application at present. But even in this case, I mean, the outliers are higher. Also, you have to consider that those are really large basis sets that will probably give you already considerable numerical trouble if you would, for instance, use such a big basis set for some kind of cluster, right? You would run into over-completeness problems and so on. So the second basis sets are now the numerical atomic orbitals. And actually, you see that they are doing much, much better. I mean, if you use kind of standard production basis sets like here, this tide, you see that on average you are already much below 1 kilocalorie per mole. And in the worst case, you are a little bit worse, but not significantly. Also, what has to be considered is that, I mean, those results here kind of indicate that with the numerical atomic orbitals, kind of you get probably in more or less all cases the precision that you want to obtain before you run into problems of numerical instability, whereas with the Gaussian basis sets, I think probably you will run into numerical instabilities in most cases long before kind of you can achieve this famous chemical accuracy of 1 kilocalorie per mole. Yeah, then here concerning the dipole moments, there you see it's more difficult. I mean, probably people would like to have some accuracy which is 0.01 dBi. You see, actually in many cases this cannot be obtained. Yeah, then okay, so that's my last slide. Now just still the errors in pseudopotential. Also, it turns out that kind of widely used pseudopotentials give really astonishing large errors. So I have here plotted several pseudopotentials. So those are those optimized norm-conserving Vanderbilt pseudopotentials from the Abinit website. Here, those are pseudopotentials, for instance, that are available within Quantum Expresso. Then we have those old FHA Tooley-Martins pseudopotentials, and then here our pseudopotentials, which are the default pseudopotential in big DFT, but can also be used in other electronic structure codes. And finally, here still an ultra-soft pseudopotential. So you see that all those pseudopotentials, we are glad, with the exception of kind of the ones that we are using, kind of they can give, at least in certain cases, rise to errors in atomization energies also which are much larger than the intrinsic limitations actually of the PBE functional. Yeah, that brings me to the end of my talk. Just here is still the list of the people that are involved, and I'm happy to take questions now.